Thank you. Yeah. So suppose we want to do community detection on this network on airports, and we use the Louvain community detection method. Then we get this, which correctly detects Chile, but splits Argentina up into 3 communities. But modularity also comes with a parameter called resolution parameter, and if we just slightly change it, then we do get the correct partition. So many community detection methods turn out to have like that they need to be tuned to get partitions of the right granularity, and if you don't do that, then you tend to get partitions of the wrong granularity. And so that is a problem that we will discuss in this presentation, and that we will find a heuristic for that works for a general class of community detection methods, which includes the modularity maximization. So in this work, we build on previous work where we have introduced this general class of community detection methods. And so I will briefly introduce it in the next few slides. But in short, this is a sort of geometric viewpoint of community detection, where partitions are represented as points on a hypersphere. And then what we do is we map the network to a point on the same hypersphere. And then to find the communities, we simply find the partition that is closest to this point where we mapped the community to. But then, of course, the question is like, how do we choose which point to map the network to? And that is a very general problem. And in this presentation, we focus on one dimension of this, which determines the granularity of the partition that you'll get. Yeah, and so we derive a heuristic for this, to choose this dimension, and we do this by some hyperspherical trigonometry that you might see later in this presentation. So what does this geometry look like, this hypersphere? So first we represent partitions as a binary vector. So this vector is defined as follows. So it's indexed by the vertex pairs. So that means that the dimension is already n choose 2, which is quadratic, so very large. And then each entry is 1 if both vertices are in the same community, and it is -1 if they are in different communities. So, for example, for this small partition, we get this 2 vector with 2 1s corresponding to the 2 intra-cluster pairs, and then 4 -1s.
Sorry, you say it's a vector, not matrix.
Yeah, it's a vector. Yeah, so you could see it as a matrix, and then we take the upper triangle, but yeah. So vector turned out to be slightly easier in the calculations.
So it's a matrix with
yeah, it's just the flattened upper triangular matrix. So it's not, we only keep the entries ij where I is smaller than j. So we don't have them twice. Yeah, so the dimension is n choose 2, which we denote by capital N. And so as you might notice, is all these entries are either 1 or -1. So each of these vectors has Euclidean length square root of n, of big N. So that means that they're all on a hypersphere. And that makes it reasonable to look at to consider the hyperspherical geometry that is induced by the angular distance on this vector space. So the angular distance is given by this inner product normalized by the length and then the arc cosine of that. So for 2 particular partitions, like namely the partition where all vertices are in the same set and where each one is a singleton, each community is a singleton, they form opposite poles. So because you either have all 1s or all -1s, and they're on opposite points of our hypersphere. And so we define the latitude of a point as the angular distance to this -1 pole. And so this is, of course, inspired by geometry. So you might recognize that ball over there. So if the vector is a clustering, then this latitude is given by this function, which only depends on MC, which is the number of intra-cluster pairs. And the number of intra-cluster pairs is a measure of granularity of the partition. So equivalently, the latitude is also a measure of granularity for these partitions. So if the granularity is close to pi, then it means that you have large communities, and if it's close to 0, then you have small communities. And also on like our globe, we have parallels and meridians, and we also borrow these terminologies. So a parallel is a surface of constant latitude. So basically all the vertices that have a certain latitude. And if you have, and then of course, if you have the latitude pi over 2, then that is basically the equator. And if you have any point and you want to project it to a given latitude, then that can be done by a parallel projection. And this expression might look a bit complicated, but the only thing that you know is that we only need to add a constant and renormalize. So it's easy to compute this. And then the meridian is a geodesic between the 2 poles. So it's on the globe it's a vertical line, and in our case it's just it can be parameterized by this parallel projection of any point, and then for all the possible latitude values. And then one other thing that is defined on this geometry is the angle on the surface of the sphere. So here in this drawing you see visually how it is computed. So you project basically to the tangent plane and just compute the angle there. And the formula for that looks a bit like this. And so for example, if you take 2 points and then take the meridians of these 2, then they will meet at the poles. And then the angle that it makes on those 2 poles, we call the meridian angle. So that is given by this formula. And what turns out, interestingly, is that this meridian angle is actually equal to the R cosine of the Pearson correlation between these 2 vectors. So if you take 2 vectors, then they are Pearson correlation, the R cosine, then that is exactly equal to the angle that these points make at the meridian. And this is very convenient because, like in prior work, we looked at all kinds of cluster similarity matrices of indices. So that's measures to measure similarity between partitions. And there, like this correlation coefficient was one that satisfies almost all the properties. And then one of the nice properties was that if you take the R cosine, that you then get a metric distance. But that's for another time. So that's why we call this angle on meridians correlation distance for the rest of this talk. And then, the other nice thing that we discovered in this geometry is that modularity maximization can actually be nicely interpreted in this way that I described. So you map the network to a point in this geometry, and then the angular distance between that and the partition point is actually equivalent to the modularity, like in the sense that if one partition has a lower distance than the other one, then the modularity of the lower one is higher than the second partition. Yeah.
Is the number of communities related to this latitude?
Yeah, so yeah, the number of communities is also a measure of granularity. But of course, like it doesn't say anything about how large these communities are. So you can have like a community of size n over 2 and then n over 2 communities of size 1. And you'll still have relatively many intra-community pairs, and so still a relatively high latitude. But yeah, if the latitude is larger than pi over 2, then you have at least one community of size larger than over 2. And yeah, there's some, you can give some lower bounds of the number of communities that there can be, and based on this latitude. Yeah, so this, the way that you map the network to a graph is simply the sum over here of the all1 vector, and then this binary vector over here, which is similar to this partition vector, but then simply like the edge connectivity. And then here, this degree product. And then the resolution parameter is over here. Yeah, and this also works for other versions of modularity. For example, where the null model is simply the Erdős-Rényi null model, that also works. And yeah, basically any other null model that you can come up with will also work for this. Yeah, so that tells us that modularity maximization fits this framework that we are discussing here. So yeah, so we define the class of methods that fit in this framework as projection methods. So because what we do is basically we take a graph, then we project it to a point on this hypersphere, which is then projected to the nearest partition. So it's two projections, so that's why we call it that. This maximization step can be performed by the Louvain algorithm. And so this Louvain algorithm is originally only given for modularity, but it can quite easily be adapted for different vectors that you want to minimize to. And so this vector by which you represent the graph, we call it the query vector, because you're sort of simply querying the nearest partition to that. And yeah, so we denote this result of the Louvain algorithm, so like an approximate nearest partition to a given point by L of Q. So like you can depict it by a diagram, like we start by a graph, and then we map it to a point, to a query vector, then we apply Louvain and get, or any other algorithm, and get a clustering vector. But of course we don't have to use this modularity vector. We can basically use any kind of vector that we want. So the simplest other alternative would simply be this edge vector, or the wedge vector. So we call it the number of common neighbors between each vertex pair. So that's the number of wedges that are between 2 points. But if you would simply feed this into Louvain, then what you get is generally a partition of the wrong latitude. So for example, for this wedge vector, you know that it's always non-negative. So there's never a reason to not put two vertices in the same community. So the maximum of the clustering and minimal distance is almost always the one where everyone is in the same community over there. So one way to get around this is adding a constant to each entry of the vector. So this is like the simplest approach that you could do. And this transformation is actually equivalent to simply changing the latitude of the vector. So you take this vector and then you choose another vector on the same meridian. And so basically the problem that we are going to tackle in this, the rest of this presentation, is how to choose this latitude for a given graph or setting. So for that we will give a heuristic, which is, yeah. So first the objective what we want to achieve by this sort of choice of latitude. Of course, ideally, we want to have that the partition that we get, like the communities that we detect in the end, are as similar as possible to the true, to the ground truth, if there is any. But this is, of course, quite ambitious of a goal. So we opt for a simpler goal, which is namely that the granularity of the resulting partition is the same as the granularity of the true partition. So because we are simply tuning this parameter which controls the granularity, so this seems like a reasonable appropriate goal to set. And the heuristic that we get out of it is this. So we have a nice formula of like how to choose the latitude, and it is a function of the ground truth latitude. So that's the latitude of the ground truth partition. And then here, the correlation distance between the vector that we start with. Yeah, this question?
Sorry, maybe I missed something. You know the latitude of the ground truth partition?
Yeah, so that's what I was just, yeah. So this is a bit similar to other methods. You need to put some data in, and so this heuristic uses that information, but there is also a way to get around that by if you don't know the ground truth. But so for this case, we assume that we know it, so that we have this this nice formula. Yeah. So here we this lambda of t is the ground truth latitude, and then this theta is the correlation distance between the vector that we start with and the ground truth vector. So this is basically a variable that says how well is our data correlated to the partition that we want to find. So for example, if this input vector is simply the edge vector, and if you have very few edges between communities, then that means that this correlation tends to be quite, then this correlation distance will be low. And so if you see this formula, then you can also try out different values of theta. So for example, if we would have theta 0, which means that it's perfectly correlated with it, then this one is 0 on the top, and this one is 1, this one is 0. So then you just get the R cosine of the cosine of lambda t, so that you get simply lambda t as the latitude of our query vector, which is also desirable because then basically the vector that you put in is already the partition vector that you want to find, the clustering vector. And if you have completely uncorrelated data, then so if you have so if you have this theta equal to pi over 2, so that means that the correlation is 0. What you get then is the R cosine of 0, which is pi over 2, which is then equivalent to resolution of it's kind of the same as a resolution parameter of 1. Yeah, but so here this formula does assume some knowledge of the ground truth partition. But later on you will see how to get around this if you don't have this, this information. But the point here is that if you have this information, then we have this very nice formula over here. And you can also test that with, for example, stochastic block models, and it works surprisingly well. Yeah, so then, or the pipeline changes slightly. So we have a graph over here, and then we have some way to turn that into a vector. So that could be like the edge vector or wedge vector. And then we apply our heuristic to get a query vector. And then we put that into the Louvain algorithm to get a clustering vector that is supposed to be of the correct granularity. So this is an illustration of of the claim. So what we plot here is the latitude of the partition that results from for different latitudes of the query vector. So over here we have the latitude of Q. Then here on the y-axis we have the latitude of the candidate clustering. So our claim is that if you choose the lambda equal of the latitude equal to lambda star, then you get clustering latitude close to the true one over here. And as you see, this blue line intersects this red cross quite precisely. And so this left-hand side is where we use the edge vector. And then on the right-hand side, we used as input a different vector. We simply took the ground truth vector, but then added the Gaussian noise to it. So in both cases, we added quite a lot of noise to get a nice plot, because like if you add less noise, then you get like a plateau over here that's pretty wide. So then it looks quite uninteresting. So for reference, on the left-hand side, half of the edges are inside communities and half are between communities. But also the graph size is relatively small, so we have 10 communities, each of size 10. So basically this heuristic was,
What would happen if you had more noise? If you check what happens if you have more noise?
Then it's more random and less accurate.
Yeah, but why I'm asking, because like you would expect that then actually checking against ground truth should give you wrong information.
Yeah, of course you get.
This is you get in this.
Yeah, so if you add more noise, then the clustering that you get will have a more significantly different granularity than the ground truth. So.
And what I'm asking, and it is visible on those plots then, right? This is my question.
Yes. Yeah. I think later we'll have a plot that shows that. But yeah, it does. You mostly see more randomness, more variance. But yeah, also eventually it will just deviate. So the way that we attempted to tackle this problem was basically by just a lot of experiments, and then in the end we just spotted some useful patterns that we managed to exploit and turn into this heuristic from the slides before. So the thing that we noticed is that, like, as a function of like the latitude of a query vector, the point where the angular and correlation distance between the query and the true partition, where they intercept, is also the point where these two distances between the query and the candidate clustering intersect. So for a given ground truth an input vector, you can select the lambda for which these two intersect, these top two, and that's denoted by this crossover here. And if you then sort of plot these other two as a function of this lambda, then you see that they intersect at that point. Yeah. So that is also validated over here. So here we have this ground truth vector with some Gaussian noise added to it, and then here we do for different noise levels, so different values of the standard deviation. And what we plot over here using box plots is then the ratio between the angular distance of the query vector to the candidate clustering and this distance to the ground truth clustering. And so for low noise levels, you see that this ratio is basically 1, which is what we want. And then for more moderate noise levels, you see this, that there are some outliers. And for larger noise levels, you see that it's just more all over the place. And yeah, of course, the mean will also at some point not be close to 1 again, or the median. So this experiment was done for 1,000 vertices and I think 50 equally sized communities, yes?
What is the y-axis?
Yeah, so the y-axis is this ratio over here between these two things that we claim to be the same at that point. Yeah, so then we have this, we made this observation that these two hold, and yeah, that tells us that this is a property that we want our query vector to have. So what we then basically do is we check for which value of the query latitude does this hold. So you try to find this intersection between these 2 points. And that is where yeah, the spherical trigonometry comes in. So yeah, both of these functions are expressible as just a function with a lot of cosines and sines, and it has 2 solutions, and it's also like illustrated the way that we found this solution on this picture over here. So here is like our ground truth clustering, and then here is the latitude on which our input vector is. So that's like the vector that we start from, and then we want to find the point on this meridian where the angular distance to this point is equal to this theta over here. And yeah, that has yeah, to find that point, the approach is basically the same as you would do in like flat trigonometry. But yeah, the nice thing about spherical trigonometry is that it's just like normal trigonometry, but then just with twice the amount of pain. And yeah, so eventually you do get these 2 solutions given by this expression over here. And yeah, so the approach is basically you go from here to find the closest point on this meridian. So you like an orthogonal projection. And then you use Pythagorean theorem, but then the spherical variant, to find the points that are at like a given distance from that. Yeah, so then this gives 2 solutions. There's also a second observation that we use, and that basically eliminates this lower solution over here. And so then we are left with that second value, but I will not discuss this second observation because of time constraints. Yeah, so what we get is that so if we compare this to standard modularity, so the resolution parameter 1, and then another way to set this resolution parameter, and then we plot the latitude that we get as a function of the fraction of intra-community edges, we see that standard modularity goes up quite rapidly, and this maximum likelihood method stays accurate quite well, but then also deviates, while ours stays constant quite long. And if we compare the actual performance of these, so the similarity to the ground truth, they see that these 2, so maximum likelihood and our heuristic, perform quite on par. And then we also tried this out with several other benchmark random graphs, and we also like used several different options for x or input vectors, so edges, this maximum likelihood vector, wedges, and then also like a vector of Jaccard indices. And there we see that on 3 of the 4 benchmarks, one of our alternatives performs better than maximum likelihood, even though this graph is the actually generated by the generator for which that is the maximum likelihood, and still like our alternative works better. And yeah, and then there's still some open problems, but I see I already am over my time, so I'd like to thank you for your attention.
What's that maximum likelihood method?
Yeah, so that is this from the equivalence between modularity and maximum likelihood estimation. Yeah, maximum likelihood. So that prescribes one particular value of the resolution parameter, and then we just use that value of the resolution parameter. But that also requires some information about the ground truth.
So your method outperforms that method most of the time.
So in this case, the non-degree corrected case, that is, yeah, real case. But yeah, the reason for this is that yeah, this method is known to have like some bias with granularity. So it's true. It's like equivalent to doing Bayesian optimization over a uniform distribution over all partitions, and they tend to be quite granular. If you draw a uniform partition, then you get quite small communities. And so if you want to find larger communities, then you will just have a bias towards that other thing.
It's maximum likelihood, so what is the likelihood function?
Yeah, the likelihood function of the splintered partition model.